Hello students, welcome to EPG Pathshala. I am Dr. Aditya Saxena from the Central University of Haryana, Department of Physics. Today we are going to discuss about a module Angular Momentum 2 under the paper Quantum Mechanics 1. So students, let us see what we are going to learn in this module. We'll start with the matrix representation of the components of the angular momentum operator J, that is, the components Jx, Jy and Jz, which are the x, y and z components of the angular momentum operator, and the j square component of the angular momentum operator. After having studied the matrix representation, we'll then try and understand the representations of the eigenstates as column vectors on which the angular momentum operators for each value of j can operate. Then the Pauli spin matrices will be discussed, and we will see that what is their importance and what are their important properties. The present module is actually a continuation of the preceding one, wherein starting from the commutation relations of the angular momentum operators, we deduced the expressions for the eigenvalues of the diagonal operators j square and jz. In the common basis represented by the state or the eigenvector Jm, where J and M labeling respectively the eigenvalues of J square and Jz. Here J is the angular momentum number and M is the magnetic angular momentum number. In this module, we shall obtain the matrix representation for the components of the angular momentum operators Jx, operator Jy, operator Jz and operator J square, where operator Jx, operator Jy and operator Jz are the x, y and z components of the angular momentum operator. Considering a few specific values of the angular momentum, such as j equal to 0, j equal to half, j equal to 1 and then j equal to 3 by 2, we shall write their matrix representations explicitly. It is remarkable to note that the eigenvalue spectrum includes not only the integral but also the half integral values of j. As we already know, half integral values of j describe the intrinsic spin of the particle, such as an electron or a proton or a neutron. We describe the spin matrices for the spin half particles, that is, for the electrons, for the protons and for the neutrons, first introduced by Wolfgang Pauli in 1927, and briefly mention their important properties. Matrix elements of operator J square and operator Jz. Now we shall discuss the matrix elements of the operators, that is operator J square and operator Jz, which are the operators of the angular momentum. So if we look at the state vector Jm, for M having values ranging from minus j to plus j, including 0, where M is the magnetic angular momentum, then we have that the complete orthonormal basis for a 2j plus 1 dimensional subspaces, that is, if we consider all the elements from minus j to plus j including 0, then the total number of elements that we have is 2j plus 1. So this constitutes the complete orthonormal basis, and we have a 2j plus 1 dimensional subspace, which provides the angular momentum representation in which any function of the angular momentum components can be represented by a matrix which will have the elements given as, so bra J prime M prime operator A acting on ket Jm. That means it is basically the operator A and the bra elements or the bra vector J prime M prime and the ket vector Jm. And then if we solve this, then we can see that the above representation can be written as, for the operator J square, we will get bra vector J prime M prime operator J square acting on ket vector Jm, and this turns out to be equal to J into within brackets J plus 1 into H cross square delta function of J prime and delta function of M prime. So what one sees is that here H cross square is the Planck's constant, or rather H cross is the Planck's constant, and J into within brackets J plus 1 are the corresponding eigenvalues. Similarly, if we try to find out the matrix elements for the operator J, we can have a similar representation. Bra vector J prime M prime operator Jz ket vector Jm, and this gives us the final result M H cross delta operator Jj prime delta operator M prime, where M is the magnetic angular momentum number. Here the delta operator Jj prime means that if J is not equal to J prime, then this delta operator will go to 0. Similarly, delta operator M prime means that if M is not equal to M prime, then this delta operator goes to 0. And so from this, we can write for the operators J plus and J minus how we can find out their values, which means that using the values of the operator J square and Jz, we can actually find out the values of the operator J plus and J minus, where J plus is the incremental operator or the creation operator and J minus is the decremental or the annihilation operator. And the values of these can be found out by taking the scalar product of these with the ket vector J prime M prime. Matrix elements of Jx and operator Jy. So now, in order to find out the values of the operator J plus and J minus, we take the scalar product of these operators with the ket vector J prime and M prime, and the matrix elements of these scalar products turns out to be bra vector J prime M prime operator J plus ket vector Jm is equal to C dagger Jm H cross delta operator Jj prime delta operator M prime M plus 1, where C dagger Jm is a constant that we need to determine, and H cross is the Planck's constant. Delta operator Jj prime would give us a 1 if J is equal to J prime and will give us a 0 if J is not equal to J prime. Similarly, delta operator M prime M plus 1 would give us a 1 if M prime is equal to M plus 1 and 0 if M prime is not equal to M plus 1. Similarly, we can find out the matrix elements of the operator J minus by taking the similar scalar product, that is bra vector J prime M prime operator J minus acting on ket vector Jm, and this gives us the result C Jm minus H cross delta J prime delta operator M prime M minus 1. So here C Jm minus is also a constant that we will need to determine. H cross is the Planck's constant. Delta Jj prime gives us a value 1 if j is equal to j prime and returns a value 0 if j is not equal to j prime, while delta operator m prime m minus 1 gives a value 1 if m prime is equal to m minus 1 and gives a value 0 if m prime is not equal to m minus 1 and gives a value 1 if m prime is equal to m minus 1. Here the constants C dagger Jm or C plus Jm and C minus Jm, which are also sometimes referred to as the creation and the annihilation numbers, can be determined by equating the norms of the above equations, that is the scalar product equations of the operators J plus and J minus on both sides. So if we take the norm of these equations of operator J plus and J minus, that is the scalar product of J plus and J minus on both sides, and equate them, then what we find from the solution of these equations is that the number or the constant Cjm plus is equal to, within brackets, J minus m into, within brackets, J plus m plus 1 whole to the power half. And similarly, we can also find out the value of the constant Cjm minus, and this turns out to be equal to, within brackets, J plus m into, within brackets, J minus m plus 1 whole to the power half. So in this manner, we are able to determine the values of both these constants C plus Jm and C minus Jm. Now, having determined the matrix elements of the operators J plus and the operator J minus, we can find the matrix elements of the components of the angular momentum operator J, that is the operator Jx and the operator Jy. And using the relation between Jx and the operators J plus and the operator J minus, we see that the operator Jx, or the x component of the angular momentum operator, is equal to half times operator J plus operator J minus. Similarly, the y component of the angular momentum operator, that is Jy, turns out to be equal to minus half times iota times, within brackets, operator J plus minus operator J minus. Here it is important to keep in mind what we have already discussed earlier, that the operators J plus is the incremental or the creation operator for the angular momentum eigenvalues, while the operator J minus is the decremental or the annihilation operator for the angular momentum eigenvalues. Finite dimensional representations. From the above results, it is clear that the matrices representing the angular momentum operators Jx, Jy, Jz, J plus, J minus and J square are all diagonal in J basis, that is, are all diagonal in J in the basis given by the state vector Jm. Here Jx, Jy and Jz, that is operators Jx, Jy and Jz, are the x, y and z component of the angular momentum operator. Operator J plus and J minus are the ladder operators of the angular momentum operator, and we have then the J square operator. Thus, for a given value of J, that is J equal to 0, half, 1, 3 by 2, 2, and so on, we have an infinite number of representations for these matrices, having 2j plus 1 columns and rows labeled respectively by the values of m and m prime. So now there are two ways in which we can give these representations. One can either consider all these representations together to form a single representation of infinite rank, or consider each of these representations of two j plus 1 dimensions separately. These finite dimensional representations for j equal to 0, half, 1, 3 by 2, and so on for the angular momentum operators jx, jy, jz, and j square are illustrated in the text that is provided with this module. Regarding the state vectors on which the above matrix representations of the components of angular momentum J are to operate, we know that the representation of an arbitrary state given by ket vector psi with respect to the basis vector or the state vector Jm basis would be a column vector whose elements are given by bra vector Jm ket vector psi. The dimensionality of the column would depend on the values that M can take for a given J. That is, the different values that the magnetic quantum number can take for a given value of the angular momentum number J. For example, for J equal to half, M can take two values, plus half and minus half. It has two elements labeled by M equal to plus half and M equal to minus half. Pauli's spin matrices. Now we will discuss another important concept that is very useful in quantum mechanics, which is we'll try to incorporate the spin of the electron or the neutron or the proton into the formalism of quantum mechanics when we are trying to define or discuss any atom. So we all know that the electrons and the protons and the neutrons are the building blocks of the atomic and the nuclear physics. And we also know that the electron, the proton, and the neutron, all of them have a spin half. That means they are all fermions. They are Fermi particles because we all know that any particle which has a half integral spin is a fermion, and a particle which has a zero or an integral spin is a boson. So the concept of spin particles, or rather the concept of incorporating the spin of the electrons and the neutrons and the protons into the overall quantum mechanical formalism, was first developed by Wolfgang Pauli in 1927. So if we denote the spin vector by vector S, and if we write it as spin vector S is equal to h cross by 2 times vector rho, then we see all the vector sigma has the components sigma x, sigma y, and sigma z, and are called Pauli's spin matrices. That means that the components sigma x, sigma y, sigma z can be defined as sigma x is equal to matrix 0, 1, 1, 0, that's it's a 2 cross 2 matrix. Similarly, sigma y is also defined as a 2 cross 2 matrix given by matrix 0 minus iota, iota 0, and sigma z is also 2 cross 2 matrix given by matrix 1, 0, 0, and minus 1. So when we define these spin components of the spin vector sigma by sigma x, sigma y, sigma z, these components are called the Pauli's spin matrices. Now let us discuss some of the important properties of these Pauli's spin matrices. So first of all, we see that the commutation relation of these Pauli's spin matrices, which are denoted by, here we are using the indices I and j to denote the components x, y, and z. So wherever we will now be referring, wherever in the relation we will see that the indices I and j are occurring, they actually refer to the three components x, y, and z. And if I is component x, then j will be component y and k will be component z. And similarly, we can do it in a cyclical order, and accordingly we can get which component is being denoted or is being represented by I, j, and k. So here the first relation or the first important property of the Pauli spin matrices is its determinant. So the determinant of sigma I sigma j turns out to be equal to twice iota times epsilon ijk times sigma k, where epsilon ijk is a tensor of rank 3 and is referred to as the symmetric tensor, and sigma k is the Pauli spin matrix of the third component, denoting the third component. Similarly, so in the first relation, we have defined the commutation relation, that is the commutation relation of sigma I and sigma j gives us the final result twice iota times epsilon ijk times sigma k, where epsilon ijk is the tensor of rank 3 and is defined or is termed as the symmetric tensor. The anti-commutation relation of sigma I and sigma j yields twice delta operator ij, which means if I is equal to j, then the anti-commutation relation of sigma I and sigma j gives a value 2, and if I is not equal to j, then the anti-commutation relation returns a value 0. And finally, sigma I times sigma j is then given by delta operator ij plus iota times epsilon ijk sigma k, where, as we have discussed earlier, delta operator ij would give a value 1 if I is equal to j and would give a value 0 if I is not equal to j. Similarly, epsilon ijk is the tensor of rank 3 and is called the symmetric tensor. So here what is important to note is that while writing down these relations, we have replaced the x, y, and z components of the Pauli spin matrices with the ijk, each taking the values 1, 2, and 3. These relations can be easily verified if we write them in the matrix form. Now we know that there are two spins, or rather two basic spins. We know that the value of the spin is half, and the spin half will have two states, or in other words, it will have two eigenstates, alpha and beta, where alpha denotes the spin up and beta denotes the spin down states respectively. And both these spin states, that is both these eigenstates alpha and beta, satisfy the orthonormality relation bra vector alpha ket vector alpha is equal to bra vector beta ket vector beta is equal to 1. Similarly, bra vector alpha ket vector beta is equal to bra vector beta ket vector alpha is equal to 0. Now let us discuss the operations of the spin operators on the eigenstates alpha and beta. So firstly, we would follow a similar procedure as we did for the angular momentum operator, that just like we found out the eigenvalues of the angular momentum operator for the operator j square and jz, similarly here we will find out the eigenvalues of the operator s square and sz of the spin operators. And we will see that in order to find out these values, we operate these operators on the eigenstates alpha and beta, where alpha is the spin up state and beta is the spin down state. So let us see that when the operator s square acts on the eigenstate alpha, it gives us 3 by 4 times h cross square alpha, where 3 by 4 h cross square is the eigenvalue of this operation, and alpha is the eigenstate. Similarly, the operator S square acting on the eigenstate beta gives the value 3 by 4 h cross square beta, where 3 by 4 h cross square is the eigenvalue and beta is the corresponding eigenstate, and h cross is the Planck's constant times, or rather h cross is the Planck's constant by 2 pi. Similarly, the operator Sz acting on the eigenstate alpha gives h cross by 2 times alpha, where h cross by 2 is the corresponding eigenvalue and alpha is the corresponding eigenstate. Similarly, operator Sz acting on beta is equal to minus h cross by 2 times beta, where minus h cross by 2 is the corresponding eigenvalue and beta is the corresponding eigenstate. And just like we did in case of the angular momentum operator, where we defined the raising and the lowering angular momentum operators, or the creation and the annihilation angular momentum operators, similarly here also we can define the raising and the lowering operators for the spin operator. So the raising operator for the spin operator, that is operator S plus, is defined as operator Sx plus operator iota times Sy, where Sx or operator Sx is the x component of the spin operator and operator Sy is the y component of the spin operator. Similarly, the lowering operator of the spin operator, that is operator S minus, is defined as operator Sx minus iota times operator Sy, where, like we said earlier, operator Sx is the x component of the spin operator and operator Sy is the y component of the spin operator. And looking at the general relation for j equal to half, where the value of m is plus minus half, that is the magnetic angular momentum gives the value plus minus half, we get similarly over here operator S plus, that is the raising operator acting on the eigenstate alpha, gives the value 0, and the raising operator acting on the eigenstate beta gives a value alpha. That means when the raising operator acts on the spin up, it returns a value 0, and when the raising operator acts on spin down, it returns the value spin up. Similarly, when the lowering operator, operator S minus, acts on spin up, that is acts on alpha, it returns the value beta, and when the lowering operator S minus acts on the eigenstate beta, it returns the value 0, which means that when the lowering operator acts on spin up, it gives us spin down eigenstate, and when the lowering operator acts on spin down eigenstate, it returns the value 0. So from these relations, we can then obtain the operations of the x component of the spin operator and the y component of the spin operator, that is operator Sx and operator Sy. And when we operate these operators on the eigenstates alpha, that is spin up, and the eigenstate beta, that is spin down, we get operator Sx acting on eigenstate alpha gives h cross by 2 times beta, which means that the x component of the spin operator acting on spin up state returns an eigenvalue of h cross by 2 and an eigenstate spin down. Similarly, the operator Sx acting on eigenstate beta returns h cross by 2 alpha, where h cross by 2 is the eigenvalue and alpha is the corresponding eigenstate, that is the spin up state, when the x component of the spin operator acts on the spin down state. Similarly, the y component of the spin operator acting on the spin up state, that is operator Sy acting on alpha, gives iota times h cross by 2 times beta, where iota times h cross by 2 is the eigenvalue and beta is the spin down state and also the corresponding eigenstate. Similarly, operator Sy, that is the y component of the spin operator acting on the spin down state, that is eigenstate beta, gives the value minus iota times h cross by 2 times alpha, where minus iota times h cross by 2 is the eigenvalue and alpha is the corresponding eigenstate, expressing the spin operators in matrix form. So now we will see that these components of the spin operators, that is the x component, the y component and the z component, how these components can be expressed in matrix form. So first of all, we start with the z component of the spin operator, that is Sz, and we see that when the operator Sz acts on the eigenstate alpha and the eigenstate beta, what does it return? So when the spin operator Sz, that is the z component of the spin operator, acts on the spin up or the eigenstate alpha, it gives the value h cross by 2 alpha, where h cross by 2 is the eigenvalue and alpha is the corresponding eigenvector. Similarly, the z component of the spin operator acting on the eigenstate beta, that is the spin down state, gives minus h cross by 2 times beta, where minus h cross by 2 is the eigenvalue and beta is the corresponding eigenstate. So now, after having defined the x, the y and the z components of the spin operator, we can finally write down these operators in the matrix form. When these operators act on the corresponding eigenstates alpha and beta, that is the spin up state and the spin down state. So operator Sx acting on alpha gives h cross by 2, then times matrix 2 by 2 matrix 0 1 1 0 times column matrix 1 0, and this gives us the final value h cross by 2 times column matrix 0 1, and this is equal to h cross by 2 times the eigenstate beta. Similarly, the operator Sx acting on the eigenstate beta gives h cross by 2 times 2 cross 2 matrix 0 1 1 0 times column matrix 0 1, and this is equal to h cross by 2 times column matrix 1 0, and this is equal to h cross by 2 times alpha, where h cross by 2 is the eigenvalue and alpha is the corresponding eigenstate or the spin up state. So here if we look at this relation, we can see that the spin up state is given by the column matrix 1 0, while the spin down state is given by the column matrix 0 1. Similarly, writing down the y component of the spin operator acting on the spin up state alpha, we see that this turns out to be equal to h cross by 2 times 2 cross 2 matrix 0 minus I 0 times column matrix 1 0, and this turns out to be equal to iota times h cross by 2 times column matrix 0 1, and this is equal to iota times h cross by 2 times eigenstate beta. So what this means is that when the spin operator Sy, that is the y component of the spin operator, acts on the spin up state, it returns an eigenvalue iota times h cross by 2 and the eigenstate beta, that is the spin down state. Similarly, when the y component of the spin vector operator Sy acts on eigenstate beta, that is the spin down state, it gives the value h cross by 2 times 2 cross 2 matrix 0 minus iota 0 times column matrix 0 1, and this is equal to minus iota times h cross by 2 column matrix 1 0, and this is equal to minus iota times h cross by 2 alpha. So spin operator Sy acting on spin down state or eigenstate beta returns an eigenvalue minus iota times h cross by 2 and the eigenstate alpha or the spin up state. And similarly, for the z component of the spin operator Sz acting on eigenstate alpha gives h cross by 2 times 2 cross 2 matrix 1 0 0 minus 1 times column matrix 1 0, and this is equal to h cross by 2 times column matrix 1 0, and this is equal to h cross by 2 times alpha. So spin operator Sz acting on eigenstate alpha gives an eigenvalue h cross by 2, and the eigenstate is alpha, that is spin up state. While spin operator Sz acting on eigenstate beta gives h cross by 2 times 2 cross 2 matrix 1 0 0 minus 1 times column matrix 0 1, and this is equal to minus h cross by 2 times column matrix 0 1 is equal to minus h cross by 2 times beta. So the z component of the spin operator acting on the spin down state or the eigenstate beta gives an eigenvalue minus h cross by 2 and the eigenstate spin down or eigenstate beta. Here what is very important to note is that when we have tried to find out the eigenstates, the 2 cross 2 matrix that has occurred for the x component is the first of the Pauli spin matrices. Similarly, the 2 cross 2 matrix that has occurred in the formulation or in the computation of the matrix form for the y component of the spin operator is the second of the Pauli spin matrices. And when we look at the z component of the spin operator, we see that the 2 cross 2 matrix that occurs in these relations is nothing but the third of the Pauli spin matrices. So in this way we see that the Pauli spin matrices is central to the evaluation of the matrix form of the components of the spin operator, where the first of the Pauli spin matrices occurs in the evaluation for the x component, the second occurs in the evaluation for the y component of the spin operator, and the third of the Pauli spin matrices occurs in the evaluation of the z component of the spin operator, their matrix form as well as their eigenvalues and eigenstates. So students, after having gone through this module, now let us summarize what we have learnt in this module. The main points that we covered in this module were the matrix representation for the different components of the angular momentum operator J. So in that we primarily dealt with the matrix representation of the 3 x, y, z components of the angular momentum operator J, that is operator Jx, operator Jy and operator Jz, and then the matrix representation of the operator J square component of the angular momentum operator. After having learnt about the matrix representation, we then went on to the representations of the eigenstates as column vectors on which the angular momentum operators or angular momentum vectors operate for each value of J. That is, that we represented the different eigenstates as column vectors, wrote down the complete eigenvalue equation, and then after operating the angular momentum operators for each value of J, we found out the representations or the corresponding eigenvalues. Then we went on to look at what the Pauli matrices are, Pauli spin matrices, that is, when we are trying to formulate the formalism for the spin of the element, that is, we know that the proton, the electron and the neutrons all are spin half particles, that is, they are fermions. So we studied the Pauli spin matrices, which is the effective tool for incorporating the spin in the total quantum mechanical formalism. Then we also learnt about the important properties of these Pauli spin matrices. Thank you.